Good evening, 7 June 2023. The previous talk was about singularities and that they're multiplicities, and about how they reflect in the one sense what results where things go to, in the other sense the funnel, what arrives back in a sense, or the branches in the binary and digital, and the catastrophe or perestroika, or the singularity of what's the multiplicity of the other side, the multi-valued function, one of many, is like so. And there was talk about power series and operator calculus, or the order of things, and about the arrangement of indexes and addition formula, and the raising and lowering of ranks, what result making it possible to walk up and down with integer arithmetic, and the summation in indices and integers. That while of course the integral operation is all about real valued quantities, the summation is all about integer valued quantities, or that of finite differences, sometimes the finite quantities. But between the continuous and the discrete, these kinds of things. So there was the idea and consideration for different kinds of analysis, like the principal component analysis and the gradient descent, for Fourier analysis and the Taylor analysis, about the power series and geometric series and these harmonic terms. There's a discussion of the regulus, which is a way that, when it's possible to exist, that a given 3D surface can be drawn as a collection of straight lines, that there's a regulus for it, like a plane does. Or the hyperboloid, when the hyperbola is rotated, is about it's rotated through the as about the origin, where it's maintained perpendicular to the line through the identity curve. The hyperboloid of one sheet, it has a regulus that draws it, that is it. And that these are some of the kinds of concepts that came into consideration. And then much of last time I was talking about the machine model of the digital computer and the binary arithmetic of machine integers, about numerical computation in a programmatic setting of the machine, the computer. And so today, where we left off in Fourier series, this great book on Fourier series, and it's nice sometimes to see a book in the field that kind of concentrates all on one thing, that has extended context, and because it offered a solution to something that had for a long time been intractable, all of a sudden became widely applied. That after Fejer sums, there was, in the Fejer kernel, after the Dirichlet kernel, which is the other piece with these orthogonal functions that happen to be sine and cosine, and the weight function that made it possible to window and box the region under analysis to define where it's defined and well behaved and exists, the convergence of the Fourier series to values. That, rolling up to the bookmark here in the Fejer kernel, and it is indicated as by, it's in the analysis of the limit where n is large, or in infinite, fn of t of 1 over n plus 1 equals sine squared of 1/2 n plus 1 t over sine squared of 1/2 t greater than 0, and that the integral of f of n t equals pi, the integral from 0 to pi of that equals pi, for the Fejer kernel. So it's describing that, given these two properties, one describing what it is for as a function of t over the time, the other one what analytical character it has in a very particular region, here from 0 to pi, kind of like the Dirac delta is the simplest kind of notion. It's a non-standard function, though it can be approximated and built as a limit, a continuum limit of standard functions, that is 0 everywhere except to the origin, where it's infinity, but the area underneath that spike equals 1. Here it's the Fourier series is greater than or equal to 0, and then the Fejer kernel, or rather the Fejer kernel is greater than or equal to 0 everywhere, and that it's pi between this one particular region. And for any number delta such that the delta is between 0 and pi, the integral from delta to pi of fn goes to 0 as n goes to infinity. So taking this continuum limit or so, the Fejer kernel is much like the Dirac delta in that kind of sense. So using the definition of the Dirichlet kernel, the Fejer kernel equals 1 over n plus 1 sine half t times quantity sum from n equals 0 to n of sine n plus 1 half t. The sum on the right can now be evaluated using the trigonometric identity 2 sine half nt sine half t equals cosine half n minus 1 t minus cosine half n plus 1 t. Well, that's a pretty interesting identity, being that it has halving terms for sine, the argument to sine, and an offset by 1, and that it reflects as like, so this is in fact a pretty interesting trigonometric identity, and I'll be curious to look into it a little bit more and discover how it's kind of set up, because it has offsets in the substitution of parameters, and it has multiples and the scaling constant in one of the parameters and not the other ones, and on the one side it's a product and the other side is a difference. And adding the equations that result from substituting n equals 1, 3 to n in it, and that it results that it has to be under the same arbitrarily large quantity, in fact twice it, so it has to fit in this manner in the telescoping, or the way it is. That this gives 2 sine half t times this expression in the brackets, sine half t plus sine 3 halves t plus dot 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 sine n plus 1 half t equals 1 minus cosine n plus 1 t equals 2 sine squared half n plus 1 t. That is, if t not equal to 0, the sum from n equals 0 to n of sine n plus half t equals sine squared 1 half n plus 1 t over sine half t. That gives the expression for the property of the Fejer kernel. It's from formula 13. Equation 14 is a property that the Fejer kernel shares with the Dirichlet kernel. And it has that 1 over 2 pi integral from 0 to pi Fejer equals 1 over n plus 1, sum from n equals 0 to n of 1 over 2 pi integral from 0 to pi of Dirichlet equals 1 over n plus 1, sum n equals 0 to n times 1 half equals 1 half. So in terms of doubling spaces and the quadrature and the constant that results to this perfect quantity that's 1 half, and how that reflects how it's built up and out, that this kernel is splits a thing and takes half of its analytical character on the other side. The Fejer kernel and Dirichlet kernels share this property with regards to this expression, that 1 over 2 pi times the integral from 0 to pi fn equals 1 half, that the integral from 0 to pi of fn equals pi. As was already read. Finally, if 0 is less than delta less than pi, then the minimum value of sine squared half t on delta pi is sine squared half delta. And using the formula mentioned, the absolute value of the integral from delta to pi of fn should go to 0 as n goes to infinity is less than or equal to the integral from delta pi of 1 over n plus 1 sine squared half delta dt equals n minus delta over n plus 1 sine squared half delta. It is clear that the expression on the right approaches 0 as n goes to infinity. QED, as the author puts it. Quod erat demonstrandum. We are now ready to prove that for any continuous function, the sequence of its Fejer sums converges to the function. In fact, with no more effort, we can prove the following more general result. let f be a function from r to r and be a periodic function of period 2 pi that is integrable on negative pi pi. If the limits fx from the left and fx from the right exist at a point x and r, then the sequence of Fejer sums sigma sub n of x converges to the value 1/2 x from the left and x from the right at the given point x. In particular, if f is continuous at x, then sigma n x goes to fx. Furthermore, if f is continuous on negative pi pi, then the sequence sigma n converges uniformly on negative pi pi. Now this will be much like the same for the Dirichlet kernel and theorem 2.5, let f(r) be a periodic function of period 2i a greater to 0 that is integrable on delta minus a minus delta, then its Fourier series is ... converges to the value ... So then for the Fejer sums, and this is just recalling that the hysteresis and ringing up that's about the Fejer sums, how it's kind of solved up and out with this bit. Fejer sums. Now I might kind of skip past this because I'm finding it a little bit tedious to carry on, though that it does end up building up a nice diagrammatic form and helps to explain and shows good forms that come in and up and about and out of the writing of which is really just a truly classical thing since hundreds of years. The way formulas are written, and that is the big thing. Even when it's like, well, why don't we just move dx right next to the integral bar and leave what was usually otherwise in the middle at the end and gather the terms this way, you know, vis-a-vis well, if we have double integrals and we have the inside and outside, and then it ends up being what's in the middle is in the middle, you know, or those are kinds of things, some things that go into to simplify the writing, as he puts it. To simplify the writing, we shall find it convenient to define g sub x at t equals fx plus t plus fx minus t minus fx from the left minus fx from the right. That having these four quantities together and making them symbolically one, then gets into helping to explain that on the one hand, the extended thing kind of shows how they relate and a natural way of reading them, and besides that, according to the precedence of operators and parenthetical expression, that it's well defined, and that rewriting as another formula or quantity essentially guarantees that as a quantity, that it is well keeping track of that is in the scope or in the context. This is not always so clear. And so there's a lot that goes into the definition of the quantities according to what type of the quantity has, according to what kind of attributes it has, so that you can have a type of thing according to various attributes. It's a real valued quantity, that it's an algebraic quantity, that it has a membership within a completion, or it only has an existence within such a completion, or these things go into the attributes, make it so that symbolically it's one thing, that in otherwise the unfettered world of where algebraically anything can be treated according to just its non-interaction with other terms and interaction with like terms, that it ends up being that these are the kinds of things get into matters of notation, symbols and notation. Hence, we see that the right-hand side is smaller than epsilon for n large enough. F is continuous. It is possible to obtain a number of results on Fourier series from Fejer's theorem, and we prove some of these below as corollaries. In fact, even the original Dirichlet theorem follows from Fejer's, as shown in 1910 by Godfrey Harold Hardy, but we shall not see this here. See, for instance, Kar's law. Opposite pages 264 to 264. So anyways, he reads off a corollary. If f is a function from negative pi to pi to r is an integrable function, and if its Fourier series on negative pi to pi converges at a point x, which is continuous, then it converges to fx. So here it is with respect to that it's a continuous function, that if it's an integrable function, and that it converges where it's continuous, then it's like so. So this notion of the removable and non-removable discontinuities, and about the singularities, has that when the action of analysis takes up and over about the definition of what is integration or mensuration, computing the area of a planar region, or computing the area in a space of that given dimension, or having built an integral and a derivative back down, the rediffer integral, or here that when there's some talk about these continuous functions, that when they're discontinuous, that they're connected in the piecewise, say, or that's how the Riemann sums pace things over in a sense. When they're piecewise, only in terms of they still end up being Riemann rectangles. And same for Lebesgue, and then for Stiltes, that it's just kind of patchwork of those together piecewise. But then otherwise, then there's some notions about what would happen if the corner or edge case, the corner case, where it's discontinuous, would either beat up or blow out, kind of like when you have a model of soap films or viscous liquids or gases, or any kind of model of mechanics in the fluid, or the compressible and the deformable, and that otherwise the usual idea of removable discontinuities is treat them as zero, and in fact just try to get to determine how they are zero vis-a-vis some other kinds of things. And so then it gets into the notion of analysis is, well, what happens when that region becomes non-removable and it balloons up and blows up? And so part of that is just for making a secondary analysis, and it's like a binary Boolean analysis, as after Venn, to subtract the region that blows up from and according to its analytical character, the region that is otherwise occupied by this region under analysis. And anyways, this is just kind of one of the things I'm thinking about with regards to the contributions to the analytical character of these singularities, which is usually as of undefined and zero. When at the same time, for example, something like 1 over infinity in the realm where it's only exactly within this range of this completion, it comprises the analytical character range from 0 to 1, or the non-standard, the classical non-standard, or the definitive non-standard, the integral from 0 to 1 of dx. That these are the kinds of things they get into the extensions and what's beyond, and figuring out for this kind of formula that it could go without saying otherwise, if you could figure out how the discontinuous region is really a zero in this region, that otherwise that such a notion as this is like, well, we can integrate about it and get back down to derivative from that and fill it up. Then we get into some delta epsilonics and an effective infinity, or when 1 over n is less than epsilon, or vice versa, and that's carried out in the topology. And as he puts it, this can be rephrased: if the Fourier coefficients of a function that is integrable and continuous on negative pi pi are all zero, then the function is identically zero. Here he has, that's rephrasing. If two functions, f and g, from negative pi to pi onto r, that are integrable and continuous have the same Fourier series on negative pi pi, then f equals g. In that region where it exists, they're integrable and continuous. It's so bracketed down. They also have to be developed together. he says by the theorem sigma n goes f and sigma n goes g, and then f equals g. It's kind of backwards, but it is a way to relate them together, but they have to be defined so by the same development. For example, if it's two functions that were not really defined except by stacking it up to one or the other, and you figure that in a mirror copy that they'll maintain the same properties in form and proportion. But if it was right hand, left hand, and they didn't know what they were doing, it's not necessarily kind of so, because one might start a half instant later and have to use an entirely different copy of things or never count up to the thing. That if they're depending on maintaining the same telescope quantity at the same time, then they have to be the same variable. Otherwise, it's two variables, and they don't have the same value. But otherwise, it's so, and it's generally so, and it's the transitivity of equality is well defined when it's taken out after the implementation of the derivation, the result, and because there's no interaction of the terms, so it's fine. We now turn our attention to the possibility of the Gibbs phenomenon for Fejer sums, which we shall study from the following relation between the Dirichlet and Fejer kernels, that 2n plus 1 f2n equals d squared n. Well, and this is just kind of an example of the matter, is that n is not infinity, it's just a large, effectively large number in infinity. And so when we think about it in terms of this relation of these two kernels, it says under the course in development. It says while they're developing. It says where they're in the same context telescope together. And that's just to be kept in mind, reflecting on my previous comment, which now seems apropos. This equation, which follows at once from the definition of dn and the formula mentioned, permits us to construct a graph of f of 2n from that of dn, and this is as similar as where he has it for the transformation of coordinates as for the computation of the Gibbs ringing, that it was centered on the origin, and then also that it's entirely positive. Or is it f of 2n of x being the y-axis, or that, and then that the x-axis is marked for 2 pi over 2n plus 1. So he's made a sort of convention that where this function intersects the y-axis is 2n plus 1. Well, you mean 2 infinity plus 1 is like, well, it's just an arbitrarily large number, but as it goes out, it always maintains this form and proportion, or this proportionality constant, to 2 pi over 2n plus 1. So, and then we think of that, well, doesn't that look just like 2n plus 1 and vis-a-vis 1 over 2n plus 1 and all about this hyperbola and the inverse and the reciprocal? Yeah, by 2 pi, because it's a periodic function and it's brought back down for the Dirichlet kernel that's in terms of negative a to a instead of negative pi to pi. In figure 1, the author continues by squaring and then dividing by 2n plus 1. Ta-da! Note that all the ripples are now above the x-axis, and if we remember that the Gibbs phenomenon was due to the presence of the ripples in the graph of d sub n, alternatively above and below the x-axis, it follows that it should now be completely eliminated. In fact, going back to the example, in 2.6, an argument entirely analogous to the one leading to the equation 11 gives sigma n of x equals integral from 0 to x fn plus pi minus integral from pi minus x to pi of fn. For x near 0, between the interval between pi minus x and pi does not contain the origin. Then putting delta equals pi minus x and last integral above, using formula 15, we see that for n sufficiently large and absolute value x small, that sigma sub n of x is approximately 0, integral from 0 to x of fn, the Fejer kernel, plus pi. If we denote the right-hand side by phi x and the graph of phi represented in figure 2.10 can be constructed as follows. Phi is non-decreasing. Again, this is the integral from 0 to x fn plus pi, so it'll start to look like a cumulative density function or cumulative distribution function. I often confuse first the terms CDF and PDF, probability density function and probability distribution function. I've kind of set myself on calling it a probability distribution function. And the cumulative density function or cumulative distribution function, the CDF, where the CDF is a function that ranges from 0 to 1 over the domain, and it affects for a given sample whether that sample is going to be less than its value. And so any function that goes from 0 to 1 as it goes from left to right, and so it's a strictly increasing function, CDF, and it goes to 1 and it comes from 0. That is like so. And then a probability density function is any function that everywhere is greater than 0, whose integral equals 1. And then that's just the probability of any sample is the value of that function. So anyways, this function, it ranges from 0 to 2 pi. So if you divide that by 2 pi, it looks like a ramp where there's a range that from it looks kind of like the hyperbola when it comes forward, but then it actually just crosses the line and then it has this mirror image across. So what it makes is that for a small region near 0, there's the probability that sample would be linearly increasing in that region. And then it has a long tail to the right and left. So it looks kind of like a natural distribution compared to the normal distribution, which is that the normal distribution ends up being that if you take a continuum limit of a usual distributions with a centralizing tendency and a mean, they will start to look like the bell curve or the Gaussian distribution, or aka the normal distribution or the bell curve, which is humped in the center and it has tails to either side, and all these things to do with chi-squared and the standard deviations about these usual tabulated constants and all these things about 50, 85, 90, 95, 98, 99, and 1, 2, 3, 4, 5, 6 standard deviations, and the expectations of how many samples will be beneath that is very well explored and understood. So anyways, in the real world, there's a lot more of a longer tail usually. So it's a combination, according to laws of large numbers, which is what statistics represents, that if you have enough samples and you can sample without replacement, that you can find that it will appear to, that the estimates will be like so, that the samples will eventually go to the estimates. It's expected that the samples will go to the estimates. But when you have real world distributions, often they'll have a very long tail. It's called the error record or exception record sometimes. It's called that there are various laws of large numbers is usually how it's framed, because under the statistical hypothesis, kind of like so, it gets into Bayes priors and Jeffreys priors. It gets into Bayes uncertainty and Knight's uncertainty, Knightian, Bayesian and Knightian uncertainty. So anyways, this looks like a pretty natural distribution because it has a centralizing tendency and it's centered on 0, and then it would be symmetrical about that, and it just kind of has a peak instead of kind of a hump, but then and to the left and right it has a very long tail. So it's kind of like if the bell curve looks like a hat with like a round top hat and then it kind of falls off, this is the hat with a much wider brim and kind of a pointy hat. Be constructed as follows. Phi is non-decreasing because Fn is non-negative, and for n large enough, phi x is close to 0 for x less than 0 and close to 2 pi for x greater than 0. Because sigma n at x is close to these values according to theorem 2.7. So it would look like also the Heaviside step function. And what we could model the Heaviside step function when x gets small. We readily see that the overswing has been eliminated in this example. However, there is a price to pay for this. The slope of phi at the origin is phi prime 0 equals fn 0 equals n plus 1. While at the same point, the slope of the function psi equals Sn, the series number of 2.6 was found to be 2n plus 1. Thus, twice as many terms are needed in the Fejer sum as in the corresponding Fourier sum to obtain the same slope at a point of discontinuity. Here it reflects on the telescoping, and what the author has defined that why that is so is not really much. That's not given with really too much proof. It's given kind of with the heuristic in a form and a proportionality constant expressing that it's so, and saying that it's why is pretty strong, because the answer to the question word of why something is pretty strong in mathematical proof. And so here though it's kind of it cannot be not this why. It would have to be counter to the very intuition that it's a linear constant throughout all these other things, but how they're related together is part of a larger schematic framework of approach, part of a larger scaffolding. A scaffolding is what's put up about the building, the little building about the building. And it's tenuous, but the idea is that a scaffolding is set up and then tore down. So if you set up and tear down from one of these equations, then you want to reuse the scaffolding for another equation. It's independent. So you have to scaffold these two things together if they're going to be so bound by this form of proportionality and this proportionality constant. Especially when the general idea is that the value of this constant is just said to go to infinity. And it's used to make continuum limits and vanishing terms otherwise in infinite sums. There aren't otherwise really approaches to do it without being kind of like so, because these are the products of infinite sums, or as it were. Section 2.8 begins integration of Fourier series. 2.2, the Fourier coefficients were obtained, and these are the a sub I and b sub I, and they're defined in terms of sine and cosine respectively, and it's terms of x minus ct, or otherwise the formulaic approach to the substitution of the terms, and then the value that's the coefficient is the integral for each one of those. And once in possession of the Fourier coefficients, these hypotheses. Wait a second. Now, so the Fourier coefficients were obtained on the assumption that the equality in 1 held, and that term-by-term integration of this series was possible. Once in possession of the Fourier coefficients, these hypotheses were no longer necessary and were discarded. So this is where, when the scaffolding the building is up, the scaffolding is removed. That's discarded. But to build another one, you need the same scaffolding. And just as been relating about the telescoping in terms, and when they share common terms and they share common derivation, if it's so that besides that there's this fait accompli that the constants in terms are like so, and it remains in the symbolic notation, an artifact to that, representing a quantity, then the derivation of that quantity is significant. And so where it's not, then it's, and where it's irrecoverable is where that was discarded. It's a fate. It's done already. So here the author is going to get into about how to relate things when you want to kind of build up a further analysis, basically kind of like for these singularities, because it's going to be integration of infinitesimal regions everywhere. What happens if you apply a little dot everywhere and blow up that dot, and then try to integrate this Fourier series? The convergence of the Fourier series was established under a different set of conditions. At this moment, we have not yet shown whether or not a Fourier series can be integrated term by term. And as footnote reads, this follows from theorem 8.4 of Appendix A if a certain very strong condition, uniform convergence, is satisfied by the Fourier series. What we do in this section shows that this condition is not necessary at all. Well, that's rather remarkable, and it's certainly fair. When you get up to something like these weak and strong convergence and uniform and dot convergence in the respect to CMT functions and these integral MT functions, whether one would assume they're kind of the same because you figure that the antiderivative of a function exists, one could avert that there are functions that do not have a unique antiderivative, but it's kind of unlikely. But if it were so, it'd be kind of framed in one of these discontinuous type things that somehow then still is differentiable vis-a-vis how it's possible to otherwise relate in the operator calculus that functions increase in rank by any derivative and decrease in rank by the derivative in terms of the usual order of the terms, where that it is so that when you take the antiderivative of something like x to the negative 1 and it becomes ln x, and that becomes ln x minus x, and then it gets more involved, or if there is not, it's still less in terms of the value on the order of a term in the power series, that becomes more complicated in the quantities of the terms. It's still reflected that's kind of at the corner, where otherwise from the positive powers they just kind of get differentiated till they're zero, but from the negative powers then they end up getting integrated until they split out about the infinite integrals of 1 over x, which is to be explored and to be considered if they're unique. And that gets into the derivative stopping. It gets into this ideas of the impulse. It gets into this idea of making up how it's possible that if you imagine that something ends up being just perfectly tuned, that it ends up going into a box, how it can be that it was like squaring the circle or something. Now I know that sounds contrived, and it kind of is, but it's just to reflect the concept of that when given something like that, then the operator calculus can be applied totally freely above and below in the positive and negative numbers, and then makes for any other situation where it can be so contrived that those are the quantities involved, that such an integral or function or parameterization of functions, or a family of functions, or a continuum limit of an evaluation of a telescoping set and series of context of functions, that it could be pretty relevant for motion and rest, and acceleration and deceleration, and meeting and parting. So I don't know one of those in mathematics already, but I could put one everywhere is kind of what I mean. So anyways, back to this particular dedicated development. In what follows, we present a particular case of a theorem discovered in 1906 by Lebesgue, which asserts that the Fourier series of an integrable function can always be integrated term by term, even if the Fourier series itself diverges. He says it asserts, and so, I mean, oftentimes when you say assert, you mean stipulate or axiomatize. And that's the last thing you want to do in an equation. You define things and then make derivations, because any definition you've introduced brings all its baggage. And there's not much to be said for baggage, except that every following derivation has to attend to it. So the particular version that we state has been selected because it is very easy to prove and sufficient for most applications. For proof of the more general case, refer to exercise 4.11, chapter 6, okay? Theorem 2.8, let f be a function, negative pi to pi, to r be a piecewise continuous function that has Fourier series 1 half a naught plus sum n equals 1 to infinity of a sub n cosine nx plus b sub n cosine nx on negative pi to pi. If a and x are points in negative pi pi, then The integral from a to x of f equals 1/2 a naught x minus a plus sum of n equals 1 to infinity. Integral from a to x of a sub n cosine nt plus b sub n sine nt dt. Whether or not the Fourier series of f converges. So first of all, it's to be suggested that he's introduced t as the variable of integration, and for the indefinite integral, and that the definite integral is evaluated from a to x in each of these terms. With the idea being the integral of the series be the same as the integral of the function, and whether or not the Fourier series of f converges. Proof: it is enough to prove the theorem for a equals 0. What I'm looking for is about why a is less than x. If a and x are points in negative pi, so when writing the definite integral, it's endpoints. The lower one is the lower one, and the upper one is the upper one. The lower one is the leftmost one. The upper one is the rightmost one. Here he says, the general case then follows from the equation integral from a to x of f equals integral from 0 to x of f minus integral from 0 to a of f. So it just seems that it's to be understood that x is greater than or equal to a, because otherwise there's a singularity about it, because x minus a would be 0. And I suppose that's because it would be an empty region, so it'd just be like solving for the definite integral and having, fx minus fa is the same thing as fa minus fa equals 0. So it goes without saying that then, and the fact that two convergent series of functions can be subtracted term by term. Two convergent series of functions can be subtracted term by term. They have to be subtracted by all the terms. This is an arguable fact. So I guess maybe this is what he said. I'm not sure if this is what he intended when he meant assert, but two infinite series of functions have to be defined by the same things. They have to have the same scaffolding. They have to telescope the same. They can't just be two arbitrary functions, because they have to be related all the way in each of the terms and on out. So, as you can tell, I'm about outraged. I'm barely not spitting out my teeth and pulling out my hair. I'm in a variable fit and an agony of sorts about this thing. That two convergent series of functions can be subtracted term by term. Now, certainly two convergent series of functions can be subtracted term by term. That their sum is well defined is not necessarily so. It depends on the rest of the quantities, their derivations, and scaffolding to maintain in the telescoping a context where they agree. Then, to establish the desired identity, it suffices to prove that the Fourier series on negative pi to pi of the function f negative pi to pi onto r, defined by fx equals integral from 0 to x f minus 1/2 a naught x, is sigma n equals 1 to infinity of the integral from 0 to x of the usual term a sub n cosine nt plus b sub n sine nt. I thought it was reversed, but here it is, like so. Dt, and that f equals its Fourier series. to show that there exists thusly this integral. First observe that the extension of f to r as a periodic function of period 2 pi is continuous on r because f is clearly continuous on negative pi to pi, and because, recalling the definition of a naught, f of pi equals integral from 0 to pi of f minus 1/2 a naught pi equals a naught pi minus integral from negative pi to 0 of f minus 1/2 a naught pi equals integral from 0 to negative pi of f plus 1/2 a naught pi equals f of negative pi. Also, f prime of x equals fx minus 1/2 a naught at every point x in which f is continuous. That is, f prime is piecewise continuous. This is the Fourier series. I should say Fourier because the function under the integral was the function at every point at x at which f is continuous. That is, Fourier prime is piecewise continuous on negative pi pi, and by limit 2.2, Fourier satisfies conditions of theorem 2.2. Hence, Fourier is equal to sum of its Fourier series on negative pi pi. Fx equals 1/2 capital A naught plus the sum from n equals 1 to infinity of an cosine nx plus bn sine nx. For any x in R. For n greater than 0, the Fourier coefficients in this equation can be computed using integration by parts. A sub n equals 1 over pi, integral from negative pi to pi, fx, Fourier x cosine nx dx equals ... 1 over pi. The integral of this equation evaluated, Fourier x sine nx over n evaluated from negative pi to pi, minus 1 over n integral from negative pi to pi f Fourier prime x sine nx dx equals 1 over n pi integral from negative pi to pi bracket fx minus 1/2 a naught on bracket sine nx dx equals negative 1 over n pi integral from negative pi to pi fx sine nx dx equals negative bn over n. This is where it's about the a naught, and here the a sub n is like so. Analogously, the big Bn equals 1 over pi integral from negative pi to pi Fourier x sine nx dx equals an over n. Therefore, fx equals 1/2 big A naught plus sum n equals 1 to infinity of 1 over n, this quantity an sine nx minus bn cosine nx. To obtain the value of the remaining coefficient a naught, we set x equals 0. And obtain 0 equals Fourier 0 equals 1/2 a naught minus sum n equals 1 to infinity to the b sub n over n. Hence, taking this value of a naught to 16, that's formula that was read off about Fourier x, that Fourier x equals sum n equals 1 to infinity 1 over n of an sine nx plus bn times quantity 1 minus cosine nx equals the infinite sum from 1 to infinity and n of 0 to x, integral from 0 to x, and cosine nt plus bn sine nt quantity dt, QED. Theorem 2.8 is not very useful for computation because term-by-term integration of the sum of the bn sine nt from 0 to x leads to the infinite series sum n equals 1 to infinity bn over n, whose evaluation may not be possible. But one would, it does not that it necessarily converges, but in the large, its terms diminish. For computational purposes, this result can be restated in the following form: we set a equals 0. Now I'm going to leave off at this because I said I was going to look on other things for a while. Because when he said assert, then I got into my rejection of the telescoping without the interaction of like quantities and terms and the derivations shared together. At least enough that what was not discarded is kept as so necessarily. That otherwise, when he says for computational purposes, sometimes when I read that, I kind of read it skeptically when it's for computational, it's like, well, it's computational, plus I don't want to give this side of the answer, because there's a whole field of analysis that perhaps would then kind of offer for cases that have their own scaffolding, and get into, well, then there would be basically a tit for tat, or a sort of what's they called a race condition, or a case for failure of induction. Though here it's just read out is that this form can be used to crunch, and the rest of the analysis may not be possible. All right. Well, this has been pretty good. What I'd like to do is find something there here in this book a little bit later that speaks kind of some more of the historical setting, the historical content, because the author promised that a lot of his focus would be with regards to the historical setting, the historical content. And so what we've seen so far is that for the Fejer sums, for the Dirichlet sums, for the Fejer kernels and the Dirichlet kernel, they're related is to like so, and then it gets into defining how those are kind of interesting functions. We get to section 2.9, historical epilogue. Dirichlet. Succeeded Gauss. Riemann's definition of integral is applicable to some functions with infinitely many discontinuities. There are heavily discontinuous functions that fail to be Riemann integrable. The following is a classical example of the Dirichlet function. 1 if rational, 0 if irrational. Classical example given rather reluctantly by Dirichlet at the end of his 1829 paper on trigonometric series. The sum has no limit, and f is not Riemann integrable. One might aver that it is integrable, and its integrable is 1/2 x. Because if you think about it this way, just say that there is a model of the alternation of numbers dense in a region as it's 1 between an even number and an odd number, and it's 0 between an odd number and an even number as integers. So it's like a checkerboard pattern in one row that goes on out to infinity. Well, does that have an integral? In a sense, if you if for a sufficiently large region, kind of like in a lot of these integrals, it's been talked about like a sufficiently small region, that where the convergence is defined and the integral is defined, and that this Fourier series equals the function, and da da da. Here it's that for a sufficiently large region, you can kind of aver that on average you'll cover both a black and white square, and so you can take half of that as what's underneath it. And so the idea is for this is if you blow that up until such a point in time that these are essentially dense but discontinuous, these checkerboard squares, then its integral is 1/2, because basically it's like a light that's on half the time, or the duty cycle fills an area 1 in a constant rate half the time, and it's off the other half the time, and they're on and off successfully for the same amount of time. So you can model a function like Dirichlet's function if you didn't know he was talking about the rational numbers and the irrational numbers, but all you knew that he was talking about two sets that were dense in what was otherwise uniform, but that they were nowhere continuous in that analog, and then they were nowhere non-constant, I suppose, but they're NCD too. They're nowhere continuous, dense, and equally distributed. Then you might be able to look at something. Then when Dirichlet says, "Hey, here's my function that's one at even points and zero at odd points." If you integrate enough of them together, it's 1/2 of that distance on average. You can see that could be proven for a checkerboard rows for an arbitrary, that the region integration is always arbitrarily large, that it would be arbitrarily small in epsilon difference if you picked up either one of like two black boxes that have area 1 and one white box that's empty, filled in, or vice versa. That in the small enough region of integration, it would be off by up to 50%. But in a very, very, very large one, for up to 1 million rows, the most it could possibly be off be 1/1,000,000th of a row. And so it's just like when n goes to infinity, and the epsilon related would go to 0. Okay? So you could see that this function that the author is describing could be seen in a way having something that's like analytical character, and if you build a function to it, it's like this signal continuity, so that twice the frequency is enough to perfectly reconstruct it, like Nyquist and Shannon. That's what I usually associate with the Dirichlet function. Therefore, this sum has no limit as n goes to infinity, and f is not Riemann integrable. This strange function, which is discontinuous at every point, has become known as the Dirichlet function. His work on trigonometric series notwithstanding, Dirichlet's greatest achievements were in the theory of numbers, which he contributed to several important theorems, such as the fact that there are infinitely many prime numbers ending in 1, 3, 7, 9, respectively. His great work on the subject, Borlsungen-Oberzahlen theory, appeared posthumously and was re-edited 4 times. Let's see, Riemann succeeded Dirichlet. So at Göttingen, it was Gauss, then Dirichlet, then Riemann, up to about 1859, where Riemann has a chair. Riemann's work is not easily described in elementary terms. Well, I don't know about that. The notion of the Riemann sum is very intuitive and elementary. But when we get into this conformal geometry and his Riemann geometry and the Riemann metric and this kind of thing, I can imagine that they can do various different things. Writing under Gauss and dealing with complex function theory, he proved the existence of a conformal mapping of a simply connected domain in the plane onto any other simply connected domain, which led him to the creation of Riemann surfaces or analytic manifolds. These days we might call those topological invariants. Which were around. Then he got his degrees and up into the professorships and on the recommendation of Dirichlet, getting into his story, his life story. Georg Ferdinand Louis Philippe Cantor. Another mathematician interested in trigonometric series, a particular series of events leading to this interest will be explored in Chapter 3, was Georg Cantor, born in St. Petersburg of Danish descent. His father had come to Russia, family life. His interest in trigonometric series was centered on the problem of uniqueness, that is, whether or not two such series that converge to the same function of negative pi pi are necessarily identical. So Cantor was studying Fourier series, and then when I was talking before a little bit about whether the two series have the same scaffolding, so they end up making the same function in the same range and domain in negative pi pi, and where does this like so? it would have to be pretty highly contrived, but it gets into this notions of like the Dirichlet function and the continuous, as was kind of stated. What would be the consideration why that would be so? He answered this question in the affirmative. Cantor did, and so he was able to show that uniqueness still holds if the convergence is given up at a finite number of points. Cantor was ambitious and found these results short of what he wanted to do, namely to allow the convergence to fail at an infinite number of points and still be able to conclude uniqueness. But then what kind of infinite set of points should this be? Surely not every infinite set is a likely candidate. And then he talks about the limit point or the critical point, but that's pretty familiar as a focal point. But it's nice. It'll be nice to get in that later. Cantor, of course, is most famous for the Mengenlehre and the set theory and the uncountability theorems about quantification about the power set and the exponential, but the relation therefrom in the predicates, what result for set theory, uncountability and all that kind of stuff. Of course, that's addressed here in terms of the Cartesian and non-Cartesian functions, because by the time that came around, everybody assumed that all functions are Cartesian. So for a function not to be Cartesian, it is not necessarily so different from classical functions, and it fits under a lot of them. But it's something to be addressed later. Hey, well, have a great day. It'll be interesting to get into some more of the context and the surrounds about this time when Gauss, then Dirichlet, then Riemann, and then up to Cantor sat in Göttingen and started to figure out a lot of what came up after Cauchy and Weierstrass for analysis, what goes into from Fourier's analysis, which comes up and out of infinite series and their treatments, and which is a combination of the works that's come out of the Gregory and Maclaurin and Newton and Taylor, and coming out in the methods and power series, then trigonometry. Then I'll be interested to find about that one relation in the trigonometry that's like a half angle formula times a product formula that equals a difference formula in the complementary orthogonal term. Because again, this is a similar type thing that makes up for some kind of addition formula that makes up for any kinds of orthogonal functions, coordinate weight functions, that would be a neat rule to figure out a template. So that as a scaffolding, it builds the thing. Anyways, have a great day. So.